Welcome to Brain Vision.
Okay, so for this question, we need to set out the energy balance equation here, which is E dot in equal to E dot out. And if we expand it, we have Q dot in plus M dot H1 is equal to M dot H2. Q dot in here is the rate of the heat transfer to the cooling water, okay? And M dot here is the mass flow rate for the cooling water, and the H1 here is the initial enthalpy for the cooling water. And H2 here is the final enthalpy for the cooling water. If we do some arrangement here, we have Q dot in is equal to M dot times H2 minus H1, which is equal to M dot times Cp times T2 minus T1. Cp is the specific heat at constant pressure for the water, and T2 is the final temperature for the cooling water, and T1 is the initial temperature for the cooling water. And we also know that the rate of heat transfer into the cooling water can be equal to the rate of the condensation of the steam in the condenser multiplied by the heat of vaporization, okay, according to energy conservation law. Because when the rate of heat transferred to the cooling water, that means that the steam is also losing the heat from itself since it's transferring to the cooling water, okay? So now we can use, actually this one should be condensation, okay? So M dot condensation. So now we can use such equation here to substitute for Q dot in. So we have M dot condensates times HFG is equal to M dot Cp times T2 minus T1. So now we have M dot condensates is equal to M dot Cp T2 minus T1 over HFG. So we know the mass flow rate for the cooling water is given as 101 kilogram per second. And the specific heat for the water is 4.18 kilojoule per kilogram times degree Celsius. The final temperature for the cooling water is 27 degrees Celsius. The initial temperature for the cooling water is 18 degrees Celsius. And now we need to use the saturated water temperature table to find out the heat of the vaporization of the water, which is HFG here. So at 50 degrees Celsius, the heat of vaporization of the water is equal to 2382 kilojoule per kilogram. So now let's plug in back to the equation to determine the rate of the condensation of the steam in the condenser. And this can be equal to 101 kilogram per second times 4.18 kilojoule per kilogram times degree Celsius, and then times the temperature change, which is 27 degrees Celsius minus 18 degrees Celsius, and then over the heat of vaporization of water, which is 2382 kilojoule per kilogram. And this will give us the rate of condensation of steam in a condenser is about 1.595 kilogram per second. And this is the answer for this question.